Okay. I will hit the light. So today we're talking about the natural base of E. So E is maybe kind of something weird because we're not used to seeing E. But when we see E, it's just like when we see pi or any other like symbol or something that represents a number, right? When we see pi, we just know that that's 3.1415. Yeah, all that stuff. And E is the same way, except it's not 3.14. Okay? E is just a ratio that we're going to look at, and it just represents a number. So when we see E, we can think that it is a number. Also, if you look at your calculator, if you hit second on the left-hand side towards the bottom, second ln, that would be how you get the exact value of E. Second ln, second, and then towards the bottom on the far left side, like the third or fourth one up, second ln. Yeah, right next to 4. Good. That's a good way to put it.
No.
Second Second division mark would give you just E. So Aiden brings up a good point. If you hit second division sign, that will give you like just E. But most of the time, when we work with E, it's E to the something, to some power. So if you hit second and then right next to 4, then that will just go E and then to the, and I'll let you put stuff in the exponent right away.
Then I can just do like my way and then just do the power.
Yeah, that would work too. Yep, that would work as well. So a couple different ways to get there. But that is how we find E. Warm up. Good warm up, everyone. Learning targets. Students will be able to define and use the natural base of E. So we're kind of working on a definition of E already, but we're going to expand on that. And then we will be able to graph the natural base. So we're going to work on graphing what E looks like. And we kind of already know what it is, so we're halfway there. Word of operations. We have a new term. We're going to explore something in a little bit, and then we're going to learn PERT, and then we're going to practice.
That's the one.
So first, the natural base of E. Did anyone hit second division sign and then hit enter to see what E actually was? Yeah.
It was like 2.7 something.
Right. Yep. So E is actually 2.7 something.
2.7182.
Yep. Keep going. Keep going. Okay. Perfect. That's actually what E is. 2.7 blah blah blah. And this 1 plus 1 over x to the x is where that comes from. E is the number that this graph 1 plus 1 over x to the x. E is the asymptote of that graph, so it'll never cross that E value. Now, where they came up with this, or why that's really important, I couldn't exactly tell you, but I know that that's E, and we're going to work with it, and it makes stuff happen. So, trust me. Did someone have a question up there? Yeah.
No. Okay.
So some questions that you're going to see dealing with E is they like to bring back some of that stuff that we talked about with the exponents. Okay. So when we see the letter A, e to the third power times e to the sixth, how would we simplify that?
Add in the expression.
We would add the exponents. So they still have the same base, right? Their base is just E. It's the same number. So we can just add together the exponents just like we regularly would, just like normal. Same thing over here with letter B. If we were to simplify this, we could simplify 16 over 4 to just get 4. And then we would subtract the exponents, so we would just be left with E. This last one in letter C, this is 2 to the second power. So we can distribute this squared. So we would have 3 squared e to the what?
Negative 4x.
Yeah. Wait, what?
Negative 8x.
There we go. Yeah, we can multiply it. I didn't set you up well for that. E to the negative 8x. So all our same exponent rules apply. So let's think about, this is where we are exploring, okay? So get your thinking cap on. You're ready to think outside the box a little bit. Yep. Yep. Throw your thinking cap on. Let's think about graphing this for a second. So we have looked at graphs that are in the form, we looked at exponential growth and decay yesterday, right? Yeah, good. I saw a lot of head shakes. That's good. And those were in the form a times, or y equals a times b to the x, right? And we looked at with exponential growth, we can write that in the form like this. With exponential decay, we can write it like this. Is this all coming back to you? Okay. Now we are kind of looking at the same idea here with how we are graphing e. It could be in the form y equals a to the e to the r times t. Okay? So that e to the r is kind of our b value that we're replacing, just like we replaced it yesterday. But we're sticking with that exponential form. So here's where we're really using, well, first, are we following with that stuff in the blue? We good? We have questions on that.
What's the B?
What's what?
The B.
What's the b?
Yeah.
So our exponential up here, our exponential growth, like formula, is y equals a times b to the x. That's what exponential growth, and then instead of b, when it's exponential growth, it's 1 plus r instead of b. When it's decay, it's 1 minus r.
Okay.
Right? Why did I change the x to the t? That's a good question. We did have t up there a lot of times, right? Because t represented time.
Yeah.
But there's no reason to change it. So let's brainstorm. If a is greater than 0, so let's say that a is just 5.
Aren't they both A is greater than B?
Yes. A is greater than 0, and x is going to be a variable. What are our possible options for that r value? It could be either what or what. Not a specific number. It could be positive or negative. So first let's talk about if r is positive. Okay? If r is like 6. Would this be exponential growth or exponential decay? This would be growth, right? Because e is just 2 point something something, so it's a whole number, and it's to the 6th power, so we're going to have exponential growth. Now, on the other hand, that r value could also be what? Someone said it. It could be positive or it could be negative. Now, since we have a negative 7 in that exponent, that means that we just have negative e, right? Because a negative exponent means a negative number.
No.
No!
Just really
No! A negative exponent does not mean negative number.
It's small.
It's a small number. There we go.
Yeah.
Now we're
buddy.
exploring.
Yeah, buddy.
So, that would mean we have something that looks more like that, right? Sorry, back row. Like that, right? Because a negative number means we bring that down, right? Now, would this be say x just equals 1. Would this be a large whole number? Would this be a decimal? Or could we ballpark this kind of?
Yes.
It'd be a decimal. So would it be exponential growth or decay?
Decay.
Exponential decay. Good. So depending on what that r value is, makes a difference on if we have exponential growth or exponential decay. That went a lot better than I thought because I had this backup plan here that the textbook talks about. So that a value in front will be greater than 0. Okay, we're not messing with a negative a value out in front at this point. The thing that we need to watch for to decide if we have exponential growth or if we have exponential decay is going to be that r value, like you can see up here. If whatever is being multiplied by x, if it is greater than 0, we're looking at exponential growth. If it is less than 0, we're looking at exponential decay. Does that kind of make sense based on what we've talked about with negative exponents and everything? The negative exponents are small numbers. Hopefully we can keep that a little bit straight. So, tell whether each function represents exponential growth or exponential decay. Letter A, would that be growth or decay?
Growth.
It would be growth, because we're greater than 0. Good. Second one, growth or decay?
Decay.
Okay. Okay. Sweet. Good job. Now, this is where you guys have not seen PERT yet, but we've talked about compound interest. Right? Yesterday we talked about compound interest. We said that, say in your bank account you have $5,000 and it is compounded quarterly, so it's compounded 4 times a year at a 4% rate or whatever. We looked at how we could figure out how much would be in your bank account after like 6 years or something like that. That's what we looked at yesterday. Now, continuously compounded interest is a little bit different. We use a different formula, but we're still trying to figure out how much is compounded after a certain amount of time. Okay, so you might be thinking, how do I know if I use yesterday's compound interest or if I use PERT? Well, we use PERT when it says continuously. Right? That is our keyword. Compounded continuously would be when we use PERT.
Hurt cup? Hurt.
PERT. There's no A at the end, right?
There's no perks.
No. Just PERT. So an example of this will be a little bit nicer and easier to understand. You and your friend each have accounts that earn annual interest compounded continuously. Sweet.
Continuously.
Continuously.
That's Bert.
That's perk.
Bert. Bert.
The balance, okay, in dollars of your account after 2 years can be modeled by A equals all of that. So they even give us the whole equation.
Bert was pretty cool.
Now, I couldn't tell you exactly, like it doesn't make a whole lot of sense to me either, why our equation, I mean, it starts with P, right, the principal, and PERT, and then right when we see the story problem, it switches to A, the amount, because it kind of means the same thing. But that's just how math goes. The graph shows the balance, so they gave us a graph. We're not talking about your friend. We just want to look at how to solve this. So when it says you and your friend, don't think about your friend, think about you. The graph shows the balance, don't worry about the graph, we're not talking about that. Which account has a greater principal, we're not talking about it either. But this last part, which has a greater balance after 10 years? What I want to find is what our balance would be after 10 years. So what would we do to find our balance after 10 years?
Plug 10 into 2.
Yeah, when T equals 10. Did someone find it already?
28.
That's not possible.
Well, I forgot E.
I'll do it. It definitely should be greater than 4,500. Right? Because our account, hopefully, if we leave money in the bank, that it's not just shrinking if we leave it. That would-
6,713.
6,000.
One more time.
6,713.
Any cents?
21.
21 cents. Now, you could see it would be an easy question for them to say after 6 years you have $10,000 in the bank. And it was at a rate of 5%, again after 6 years, and you could see where they would make you solve for whatever this starting amount was, whatever this principal was. Okay? So that is something that they could do. And we could just simplify this E value, because that would just be a number, and we could divide it over. So instead of, like here, they gave us that we started with $4,500. But they could kind of make you work backwards and figure out how much did you start with. Yeah, question?
So, like, it's kind of like Y, it's not like an actual variable.
Yep, E is not a variable. E is just a number. Yep. We're back to class K. It's been a while, huh?
Yes.
Can we start on?
Yep.
So we're back.
Well, how many questions are there? There's more than 3 than there's
I think there's 5. I think it's 3 slides, 5 questions.
Alright, we need one.
Does anyone need a stylized?
I'll take a style.
What? I knew it went up to number 7, but I thought I cut a couple of them out. Well, the first couple are pretty easy.